Now, so it's part 2 for our take-home test to get video help for. Let's see, I've got a long, thin bar without mass, and I have mass m here and mass m here. And this system is rotating with an angular velocity of omega. And I want to figure out what the angular momentum of the system is. Well, let's say it's rotating about a point in the middle. Okay, so that's going to be d over 2 for both of these. So if I want the total moment of inertia of the system, I'm going to have to deal with each of these things here. So these are point masses going around somebody else. So this is going to then be equal to m d over 2 squared. So that's what I is going to be for that one. And of course, this one's going to be I equals m d over 2 quantity squared. So each one is going to be then an m over 4 times d squared. This will be m over 4d squared for the moment of inertia. So that's two of them together, right? So that's then going to be equal to 1/2 m times d squared. Okay, so now if I want angular momentum, L is equal to I omega, then I'm going to substitute this in for I. So the L for this is going to be 1/2 m d squared. And I'll just multiply that by omega to get the angular momentum. And I'll put a vector hat on my L to remind us that that is a vector. So that's a pretty simple situation there. Okay, next. Now what if I have a system here? This is a freely rotating platform. It's allowed to freely rotate. And I have a bucket traveling with a beginning velocity here, v. Okay, and it's about to land on this and stick to it and stay on it. Well, I've got a momentum here, p, equaling m times velocity. But remember, we can convert that into an L. L is equal to mv multiplied by the radius when it gets to this. Okay, when it lands on it, it's going to cause it to spin around and around and around. Okay, but we do know this would be like L1. So L1, angular momentum 1, has got to equal L2, angular momentum number 2. Okay, so when it reaches there, we're going to have two different moment of inertias to deal with here. So let's call this one here. So we'll do MVR. That's L1. That's got to equal, let's say, I of the disk plus I of the bucket multiplied by omega 2. Let's just do it that way. So this would be the second angular momentum. Then we could figure out what our final, angular velocity is for this. So in this case, L is definitely conserved. But kinetic energy will not be. I'll just put it does not equal conserved. Because we have an inelastic collision. One thing's moving and it sticks to it and causes it to rotate. So that's what we have there in that situation. Okay, next question. I've got a freely rotating arm here, okay, attached to a system here that's supporting it. And I want to figure out what's my force tension in the cable here in order to keep that up. So, and keep it level. We have a force downwards here. Let's just call that force gravity there. Okay, let's say this is length L here. Okay, and length L meaning the whole length of the rod. And we have a force tension at an angle theta given at this location here. Okay, and we just want to figure out what the tension force in this needs to equal in order to keep it steady level there. Well, if this is our freely rotating point here, we can consider this as a torque downwards, and this one's a torque upwards, and those two must equal each other. So I guess I'll write it here. We have to say the sum of all torques is equal to 0. This one, of course, will be a negative torque. So I'm going to go negative force of gravity, and that's going to be multiplied by L over 2. Because remember, the weight of this looks like it comes from the center. And again, that's an L right there. Try to make that look more like an L. Okay, now that's going to be plus. Okay, now we need the perpendicular component, okay, of this force vector. So there you go. And angle theta is here. So it looks to me like we're referencing the complementary angle here. So the cosine is going to give me the perpendicular component here. So I'm going to plus force tension times the cosine of theta. And that's going to be multiplied by my whole distance L, because that's acting at the edge of this. So that's how you would figure out the tension force, okay, in that cable. So nothing too difficult. Now the second part of this question, what if this rod were to allow it to freely rotate downwards? So let's say we cut this, okay, and the rod is going to be freely going down here. So that'll be what our next question looks like. Okay, so now let's take a look at that situation where we have rotated this downwards, and we're at an angle theta right here. And we need to calculate the angular acceleration at this point here. Well, we still have force gravity downwards. And the moment of inertia of this needs to be given to you. I is going to equal 1/3 ml squared. So we have torque about this now, only because of force of gravity. So where is the triangle looking at right now? So let's go ahead and do a triangle here. Our angle theta, okay, for this triangle is actually going to be located right here, angle theta. And this is our perpendicular force here that's acting, okay, on this lever arm. So that is going to be equal to force gravity sine theta. And the torque generated about this then would be force gravity sine theta, okay, multiplied by L divided by 2. The length of the rod divided by 2. So how do we calculate the acceleration for this? Well, torque does equal I times alpha. So this is our torque, and this is our I. We just substitute all that in, and then we can find what alpha is equal to. So I'll set that up for you. So we'll have then force of gravity times sine theta times L divided by 2 has to equal 1/3 ml squared multiplied by alpha. Okay, remember force of gravity is mg, so you can get things to cross off and then simplify this and solve for what alpha is actually going to be. So that's how you deal with that question. And one more final question. How to find the center of mass of a person when you put the person on two scales. Okay, so here's a person laying on a scale here, and then at his feet is another scale. So the way we do this is identify, we can call this one maybe force normal 1, and call this one force normal 2, and that's what the scales are weighing here, or determining. And then let's just call this the force gravity of the person. Remember, all of his gravity is going to look like it comes from one point, the center of mass of the person. So let's just call that this right here. Okay, and of course, we'll know the length from here to here. Let's just call that length L, back and forth here like that. And let's call our distance going from here to there just x. We just don't know what that is. Okay, let's make a point of rotation right at the person's head right there and deal with torques. So there's a torque generated from the point of center of mass of the person, and there's a torque generated from the point at his feet. So the sum of all torques equals 0. The torque generated by this is going to be 0 since that's the point of rotation. That's going to equal force normal 2 multiplied by L. That's going to be positive torque, minus force gravity times x, and we don't know what x is, and that's negative torque because that causes rotation downwards, and all that equals 0. and you can quickly solve for x. Okay, so hopefully this helps you on your take-home test, and there are other videos I will reference for the short answers.